Hello, everyone. Thank you for attending my talk today. My name is Alex, and I'm hands-on software engineer at Google, and I actively use gRPC. And today I'm going to share with you why using gRPC can be beneficial for you and your project. If you have any questions, my Twitter handle is on the screen. My DMs are open. Send me a message or tweet me. I'll answer all the questions. Or you can hold your question until the end of the talk. We'll have some time for Q&A. And first of all, what is gRPC? As you know, in microservices world, every client call results in hundreds of network calls between backend services. To make all this inter-process communication efficient, Google developed its own framework for remote procedure calls, or RPCs, and it's called Stubby. Stubby was used inside the company for many, many years. A new generation of Stubby, called gRPC, was open sourced in 2015. It's built with all the scalability, performance, and API lessons learned by years of using Stubby. It went in GA last year. Current version is 1.2.0. It's stable and production ready. Here you can ask why Google decided to reinvent the wheel. Why didn't it take some of the existing approaches like REST over HTTP? Let's look at a simple example. Google Cloud PubSub team used to provide their client libraries built with JSON over HTTP. Last year, they open sourced new version of their client library, gRPC. And their benchmarks demonstrated up to 11 times throughput improvement per CPU, just by switching their client library from JSON over HTTP to gRPC. And you can say it's unfair to compare text protocol with binary protocol, and you're right, it is unfair. But gRPC gives you this improvement out of the box. And talking about performance, Google is believed to handle billions of remote calls per second. But you know what? Forget about this. Why would you care? You probably don't, do you? Because what is important for you is how many QPS you can handle, not Google does. When you split your monolith to multiple services, all these calls that used to be in process are remote now, and latency and throughput are kind of important. So what QPS you can achieve? gRPC makes this question very easy to answer. gRPC team continuously running performance benchmarks. If you follow a link on the slide, you can find real-time performance dashboards for the latest available release and for the latest development version and master. It's tested for multiple languages, 4 operation systems, 7 compilers. And you can see in the dashboards that with gRPC Java, for unary calls, you can achieve over 140,000 QPS on 8-core machines, or even over 500,000 QPS if you use 32-core machines. Actually, it's not the highest QPS you can achieve, but we will talk about this a little bit later. What is important is it is not something that was measured once and published. It's something that is measured for every single pull request. And for gRPC team, it helps to identify any performance regression as soon as possible. But for us, for gRPC users, it helps to understand what throughput and latency we can achieve using gRPC. And when we upgrade, when we take new version of a library, we always know what to expect. We know that performance was not degraded comparing to the version we use. It gives you predictable performance. And one of the main sources of gRPC performance is its network protocol. gRPC works over HTTP2, or you can call it H2, which is a new version of HTTP protocol released 2 years ago. H2 is an evolution of Speedy network protocol, originally developed by Google. It was designed to address some of the fundamental issues of HTTP1 or H1. And for the sake of time, I will not deep dive into it, but let me just mention some of the main changes in H2. H2 is a binary protocol, unlike H1. H2 can reuse single TCP connection for multiple HTTP connections. Binary flaming layer in H2 helps to address head-of-line blocking that was an issue in H1. It has efficient header compression mechanism called HPEG that helps to reduce protocol overhead. And it has some other features like server push and stream prioritization. And to demonstrate the difference between H1 and H2, we can go to slides like httpdemo.io. And what you can see on the slide is the very same image, divided into 180 tiles, loaded with H1 and H2. And gRPC uses HTTP2 as a network protocol, because performance is a first-class citizen in gRPC. So performance is the #1 reason to use gRPC. But it's not the only reason. And we will talk about other reasons today as well. But now let's see how to use gRPC. The first step is to define a gRPC service using protocol buffers, or protobuf. Protobuf is a binary serialization protocol from Google. In fact, gRPC is payload agnostic, so there can be other implementations. But existing implementation from Google is based on protobuf. It's actually based on protobuf 3, which is a new version of protobuf that went GA last year. Let's see how simple weather service looks like. We have to create a file called weather.proto, and using protobuf define an RPC method. Let's have getCurrent method. It takes a request and returns a response, pretty simple. And protobuf allows you to define some custom options, like what will be the Java package when you generate classes from it. And we have to define our response, request and response messages as well. Protobuf supports many standard simple data types and allows you to define your custom structures or messages. Our weather request message has a field coordinates with latitude and longitude. And our response contains temperature and humidity, where temperature is a message with degrees and units. When we define the field on protobuf, we have to specify its type, its name, and its number, or index. The syntax will be used to encode a field into a binary format. We can even rename the field, and this change will be compatible as long as we keep the same index. Now we have service definition, which is a contract of our service. And we have to use gRPC runtime to generate classes from it. We can do it from command line, or we can use build system plugins. There are plugins available for Gradle, for Maven, and for Bazel. After we run it, we see generated classes for all the messages we defined in our IDL and builder-slam. And we see weather gRPC class. Inside weather gRPC class, we can find service definition, which is an abstract implementation of our gRPC service, and factory methods to create client libraries, or stubs. Next, we have to implement gRPC service. To implement gRPC service, we have to extend weather impl-based abstract class and override its getCurrent method that we defined in our IDL. GetCurrent takes a request and stream observer of the responses. And stream observer is one of the key interfaces in gRPC. It's used by both client and server for sending or receiving messages. It has 3 methods: on next, on completed, and on error. If we want to send a response to our client, we call on next with a response message. If we want to send an error, we call on error with an exception as an argument. And we can call on completed when we want to complete the stream. The simplest implementation will look like this. We use a builder to create a response. We pass it to on next method, and we call on complete to complete the call. Next, we have to create gRPC server. We use Netty server builder. We set port, we add service, and we call start. Here we could add multiple services if we have them. For this purpose, we would call add service multiple times. Then we add runtime hook to shut down our gRPC server when process is terminated. And there are many ways to configure gRPC server. We could add interceptors, service discovery, load balancing. We can configure thread pools, and so on. This is just the simplest implementation. Server is ready. Let's add some clients. It's pretty simple. We use Netty channel builder for address build, and we created a channel. Channel in gRPC represents a logical connection between client and the service. Using channel, we can create client libraries, or stubs. We don't have to write our client libraries manually anymore. gRPC generates statically typed libraries for us. And there are 3 types of client libraries, or client stubs in gRPC. Async client, we can create it with method new stub. Blocking client, we create it with new block and stub method. And future stub. Future stub is an async stub as well, but it has an API based on futures. And don't worry, in real life, you will most likely use only one of them, not all three. The simplest client to use is blocking client. We send a request, and we wait for the response. This code is easy to use, but it blocks the current thread. And it's far from being ideal if you call it from another microservice. And for this purpose, we have async clients. Async client takes a request and stream observer of the response, which is a callback. And this stream observer has the very same three methods: on next, on error, and on completed. When server sends us a response, we will get it in on next method. When request is completed, on completed method will be called. If request failed, we will get an error in on error method. It's important to understand here that when we call client getCurrent, our current thread will not be blocked. It will continue its execution, and we can send other request or do something else from the very same thread. And when we have a response from our server, on next method will be called from another thread, not from the thread we send our requests from. This approach allows us to scale number of requests in flight beyond the number of threads in our thread pool. And that's everything we need. We wrote our server. You see it on the slide. Oh, you see client on the slide, sorry. And now you see service on the slide. But you will tell me, you know what? This is not very useful, because this is not how you write your microservices. In real life, your microservices have downstream dependencies. You call other microservices, you call data storage, you call other endpoints. Your weather service can call temperature service, humidity service, and wind service, and these services will call other services. Does it look more realistic now? Let's have service definitions for these downstream services as well. The services will have getCurrent method, same as weather service. They take coordinates and return temperature, humidity, and wind. But our request response didn't contain wind. We need to add it. We add wind with index 3 to our response message. But our existing clients, they don't know anything about this new field. And they can be deployed already in other microservices or in mobile clients. Will they all break? No, because in Protobuf 3, all the fields are optional. Your old clients, if they don't know about the field, they will just ignore the field. They will not fail. They will fail later, and not due to gRPC. And this is how Protobuf and gRPC give us backward compatibility. Let's see how service will evolve. The simplest implementation we can think of will use blocking clients. We inject blocking stubs for all three downstream services to our constructor. And just call them one by one in our getCurrent method. Then build a response and return it to our client. It looks simple, but there is a problem in this code. It's sequential. We have only one outgoing request at a time. Our latency is the sum of all three request latencies. It's slow. And it blocks the current thread, which is another issue. Let's do it in a non-blocking way. We can use future stubs or async stubs for this purpose. Let's use future stubs because we haven't seen how to use them yet. We inject them. And then, in our getCurrent method, we send three requests in parallel. When we call getCurrent method on a future stub, it will return us a future. It's a Guava future. This future will be completed when a server has a response for us. Then we map this future to a new future using method futuresTransform. We transform a response from our downstream service to weather response. And again, it will be executed only when we have a result. Same with all three downstream services. Then we take all these three futures and collect them into a single future using method allAsList. We have responses future, and it will be executed when we have responses from all three downstream futures. And we add a callback on the responses future. And when we have results from all three services, we send the result to our client. So what we did, we sent three requests in parallel. We collect their results, And when they're ready, we send a response to our client with all these 3 results combined together. You can ask me, how could we send 3 parallel requests from a single execution thread? What thread will make all these I/O calls? What threads will be waiting for an I/O? To answer this question, we have to go back and see how we created the stubs. We used Netty channel builder. And for the server, we used Netty server builder. gRPC Java implementation is built on Netty. And Netty gives us asynchronous and non-blocking I/O. Netty has an abstraction called event loop. There is a thread that handles all I/O events in an endless loop. Number of these event loops is pretty small, and it's usually close to the number of CPUs available to your process. When a new message arrives from the network, event loop reads the message, and it doesn't process the message itself, but it submits the message to the worker executor, which is another thread pool. And the executor will process the message. When executor wants to send some data to the network, it creates a message, gives this message together with a callback to the event loop, and it doesn't wait for the response. Event loop writes the message to the network, and when it receives an asynchronous response, it will return this response to the worker executor using provided callback. This approach of multiplexing connections on a single I/O thread allows us to decouple I/O from waiting threads. And it scales way much better than thread per I/O. If you go back to the service that we wrote, you can ask me, why do we need to call onCompleted after onNext? Doesn't onNext mean we send all the data to our client and stream can be closed? Can we call onNext multiple times before calling onCompleted? Let's see. A long time ago, even before HTTP was invented, Heraclitus told people that everything flows, and it still does, because the world is not static. And the weather changes, unfortunately. Temperature, humidity, and wind, they all change, and they all change independently, more or less. What if we could subscribe to these changes rather than pull them? In gRPC, we can add stream modifier to the response, and we will get streaming services. Now, service can send multiple responses to the same request. As soon as value changes, we can notify our client. But our request is not static as well. We can change our location, and we want to be notified about the weather in new location. So we can add stream modifier to the request as well. Now, client can send an updated result or multiple results. And we probably have to rename our methods, because technically they're not get current anymore. They are observed now. So what do we have now? We have bidirectional streaming. Client can send multiple requests, and server can reply with multiple responses. In general, there are 4 types of API in gRPC. Unary call, when you have one request, one response. Server streaming, when you have one request and multiple responses. Client streaming, when you have multiple requests and single response. And bidirectional streaming, multiple requests, multiple responses. Let's go ahead and implement streaming service. First of all, you see that API is changed. RPC method doesn't take a request as an argument anymore, but it returns stream observer of the request instead. For the simplicity's sake, we will call only temperature service here. We have streaming stubs for temperature service. We call observe, and we create a stream observer of the temperature response. Whenever we get this response, we build weather response and send it back to our client. And we can have multiple updates on the same stream, of course. But by this moment, we haven't sent any request to the temperature service yet. If we want to send a request to the temperature service, we have to call onNext method on temperature client stream. And this is how we do it. We return stream observer of weather requests to our client. And when client sends us a request, we will get it in onNext method. When we receive a request, we send the request to the temperature service. When client completes a stream, we complete a stream to the temperature service. So this is how the simplest implementation of bidirectional streaming service looks like. And since gRPC uses HTTP2, if you have multiple streams between two services, between weather service and temperature service, all these connections can reuse single TCP connection. And you probably have use cases for bidirectional streaming in your projects as well. Use cases can include messaging applications, real-time leaderboards, sport results, market quotes, data from your smart home devices, and many, many more. Think about your project. And what is also good about streaming is its performance. Performance for streaming calls is even better than for Unary because it's much less overhead. As of yesterday, with streaming RPCs, you can achieve up to 400,000 QPAs on 8-core machines and more than 1.3 million QPAs if you use 32-core machines. And what else you can see here is that it's not only Java. You see C++, Go. And yes, gRPC supports 10 languages and 5 platforms. gRPC will generate service definitions and client stubs that can be used in all these languages. It allows you to write your services in multiple languages, and it gives your teams more freedom and flexibility. You can write prototype of your service in Python and then rewrite it for production in Go. And your clients will not even know. Their client libraries will not change as long as you implement the same IDL. And you can think that with throughput of millions QPS, we can have as many microservices as we want, right? Every single function call can be remote. But unfortunately, network issues are not limited to latency and bandwidth. In your microservices, some microservices will work better than others. Some services will break, some others will be slow. There will be network failures, and so on. Because every network call is an integration point anyway, even if it's blazingly fast. And integration points are considered to be #1 killer of your software systems. When we build a service that interacts with other services, our job is not to eliminate all possible sources of failures, because it's impossible. Our job is to be able to protect our service from these failures. And to be able to do it, we should follow some simple rules and techniques. And today we will talk about some of them. First of all, it's a very obvious rule from Captain: use timeouts. Use timeouts for every integration points of your application. Timeouts isolate failures and help to protect your service from other service failures. But using timeouts properly is not as easy as it sounds. Let's say your client calls your gateway service, which is blue on the slide, with a timeout of 200 milliseconds. And blue service makes 3 outgoing calls. It calls red service, yellow, and green, and these services call other services, and so on. What timeout should we use for these calls? The simplest way is just to apply this default timeout to all network calls. Will it work? If all our downstream services are fast and latency is low, it will. But what if not all of our services are fast? We have our client call with 200 milliseconds timeout. And it takes 30 milliseconds to call the first service, 80 to call the second, and 100 more milliseconds to call the third one. What happens? It's 210 milliseconds total. Timeout on our client exceeded. Our services have not even started to reply, but our client is not waiting for the response anymore. But services are still working because we have this default timeout of 200 milliseconds for every RPC. What happens when client receives a timeout? Very likely it will retry. But remember, our services are still busy. They're still doing this useless processing of the old request. And now they have even less resources to process our new request. And if retry fails, client can retry again and again. And these retries can overload the system and lead to cascading failures, even when we use timeouts. So default timeouts are probably not the best strategy. What can we use instead? What about trying to tune timeouts for every service in our call chain? But what should be these values? Simply decrease these values down the stack from our gateway. If you know a client will wait 200 milliseconds, we can give the first call in this chain 190 milliseconds, the second one 10, and the third 50 milliseconds. Sounds reasonable? Let's see. We have this predefined custom timeouts, and client timeout is still 200 milliseconds. Let's assume the first request takes 30 milliseconds, the second 80, and the third 25. And the last service replies in 30 milliseconds. So for the last call, request plus reply took 55 milliseconds. We already reached our custom timeout of 50 milliseconds. RPC failed, despite the fact that our client can still wait for the response. Now we have to return our client some error, probably timeout error, even though our client timeout of 200 milliseconds is not reached yet. So going back to the original question, how should we distribute timeouts? And what makes it even worse, in real life, your call topology is not that simple. In real world, it can be something like this. And we don't know in advance how many network calls every request will make. And we made another assumption. We made an assumption that we know what would be the client timeout, but oftentimes we don't. Different clients of our service can make their calls with different timeouts, and we still have to distribute this timeout somehow. So as we saw, none of the strategies were good. Let's see how gRPC solves this problem. How timeouts are implemented in gRPC. They are not. gRPC Java doesn't support timeouts, but gRPC supports deadlines instead. If you want to specify a deadline for our RPC, we can call this deadline after on client Stub. Calling this deadline after 200 milliseconds get current will make a call with 200 milliseconds deadline. But what is a deadline? Deadline is a fixed point in time by which your client is interested in the response. And if this point in time is reached, all RPCs for this request will be closed with deadline exceeded error. Let's see how it works. Our client makes a request with deadline after 200 milliseconds. If current time is 0, deadline will be set to 200, and remaining deadline, 200 milliseconds, will be sent in request metadata in a header together with the request. If our gateway spent 40 milliseconds to process the request, when it makes an outgoing call to the red service, current time will be 040, deadline still 200, and remaining is 160. And this 160 millisecond value will be sent in a header again. If a network call took 90 milliseconds and red service makes an outgoing request in 20 milliseconds, current time is 150 now, deadline 200, and remaining is 50. And if the next network call took 20 milliseconds, and the yellow service is ready to call the green one in 60 milliseconds, what do we have now? Current time is 230 now. Our client told us it would wait until 200 only. At this point, gRPC will automatically cancel all the network calls for this request with deadline exceeded status code. It won't even try to call the last service because it knows that nobody is waiting for the result anymore. And our service is happy, it's idle, and it's ready to process new requests. This is exactly what we wanted. And with gRPC, we get it for free. When we make gRPC call with some deadline, this deadline will be automatically propagated to all downstream calls, no matter how many RPCs you have on this request. And all RPCs will fail when it exceeded. And even more, on our server side or receiver side, we can check how much time we have until deadline. If we have a database call or outgoing REST call, we should apply timeout for this call because it's an integration point as well. But what should be this timeout? We can see how much time our RPC client is going to wait and use this value as a timeout to our database call. And we can even subscribe to the deadline and perform some cleanup or finish some background calculation when our client call is finished. We can use run on expiration method for this purpose. If deadline or timeout is something that we expect more or less, what should we do if our client call was unexpectedly canceled? User can press cancel button, or client application can crash, or user can lose internet connection. Plenty of reasons for the request to be canceled. A request to our service often results in multiple RPCs to other services. And if our client cancels the request, we don't want to keep all these downstream RPCs active. We want our client cancellation to be resulted in our outgoing call cancellations for the same request, of course. This is called cancellation propagation. And gRPC gives it to you out of the box, absolutely for free. You don't have to specify anything. When your incoming gRPC request is canceled, all outgoing gRPC requests made from the context of the same call will be canceled automatically. They will all fail with cancel status code, no matter how many service calls you have in this chain. And server always knows if your RPC is valid. And we can even access this cancellation status. In fact, our stream observer provides us more methods that on next and completed and an error. If we need, we can cast it to server call stream observer, and we will get additional methods, like is canceled. Is canceled returns true if our client already canceled the request. Using this API, we can even subscribe to client cancellation and again, clean up some resources, cancel non-gRPC calls, stop calculations when request is canceled. If you don't like this API, there is one more way to do it. Every gRPC call has a gRPC context associated with it. We can get it by calling context current method. gRPC context contains all these cancellation and deadline statuses, cancellation cause. It also can contain custom values. We can write data to context and read data from it. And it also allows you to subscribe to the cancellation. Cancellations and deadlines help us to prevent catastrophic failures when something bad happened. But can we have even more control? Probably even before something bad happens. Let's see what can happen if we have bidirectional streaming and server produces much more data than client can consume. Client sends a request, server has a lot of responses, it sends all them back, and if client is not able to process them all, it can fail. Stream will be closed and server will get an error. On the other hand, client can send much more requests than server is able to handle. Client sends a request, server replies with a response, and now client sends multiple requests. And if server is not able to process them all, it can fail. Now client gets an error, and stream will be closed. To avoid this kind of failures, we want both client and server, producer and consumer, to be able to negotiate how many requests each side can process. It's called flow control. If client knows how many responses it can receive, it can ask server to send this number of responses and not more. Client has a request. It can send the request together with number of responses it can handle, for example, 4. And server can send these 4 responses if it has them. And now client can request 2 more responses, and server replies with 2 more messages, and everyone is happy again. Same thing can be done in another direction. Server can tell a client how many requests it can process, and client can send up to this number of requests. And your services are happy again. And of course, for bidirectional streaming, we can have both client-side and server-side flow control at the very same time. And gRPC supports both client-side and server-side flow control. On this example, we see client-side flow control. Let me explain it. First of all, when we need flow control, we call observe method not with simple stream observer, but with its sub-interface, client response observer. client response observer extends stream observer to add one additional method before start. This method will be called before the start of a call. And its argument is a client call stream observer of the outbound stream. What we can do inside this method, we can call disable auto inbound flow control on the outbound stream. And if we do it, we enable manual flow control. Now we have to tell our client when we are ready to receive messages and how many messages we can process. We can do it using request method on client call observer. When we call request stream request 3, we ask our server to send us up to 3 messages. And when we receive these messages, we process them in the same method on next as before. On server side, we also need more than 3 methods on next, on completed, and on error. That's why we cast our stream observer to server call stream observer. And we get additional methods, including methods for flow control. We can call set on ready handler, give it a lambda expression, and this lambda will be called every time client is ready to receive a response. And we send the response from this method. We just don't send the response message immediately, we send it whenever client is ready. So that was client-side flow control. For the sake of time, I will not demonstrate server-side flow control. It's pretty similar to client-side. So flow control helps us to balance producer and consumer, client and server. gRPC supports both client and server-side flow control. Manual flow control is disabled by default. You enable it when you need it and when you know what you are doing. What else should we remember when we decided to split the monolith? Some of the things were much easier to do before we switched to microservices. Let's see how gRPC helps to approach some of these challenges. With microservices, we need a way to discover our services. And even more, we usually have multiple instances of the same service. We have to choose what instance to call. This is where we need service discovery and load balancing. gRPC allows us to plug strategies for both service discovery and load balancing into our channel. And on a high level, we still work with our client stubs as before. Our client stubs, they don't know anything about name resolution and what instance we call. For this purpose, we can provide resolver name resolver factory and load balancer factory when we create a channel. And gRPC has some simple default implementations ready for us. But if we need to customize the way we discover our services or we balance our load, we can always write our own implementations. One more challenge we will face is how to test this farm. We need a way to exercise all these dependencies without relying on network communication, because network adds latency and unpredictability to our test. gRPC gives us in-process transport implementations. In our test, we can create in-process server using in-process server builder instead of Netty server builder, and in-process channel. And we can use this channel as a real channel in our test. And now our test can include gRPC communication, but be fast and reliable at the very same time. They don't depend on the network anymore. And there are more utilities for testing, including a way to record all the values on your stream observer and some other functions useful for unit and integration testing. Tracing and debuggability is another challenge. When we have unpredictable call chain, we need a way to trace this request flow. gRPC integrates with Zipkin and Brave tracing systems. Brave is a pure Java implementation of Zipkin. Unlike the latter, it doesn't depend on Scala or Finagle. To integrate your gRPC server and client with Brave, you just add Brave interceptors that are already written for you. And of course, you need to have your Brave service up and running. And if you do it, you can trace your request in nice UIs that Zipkin and Brave provide you. And there are much more features in gRPC. including interceptors for adding some cross-cutting behavior, monitoring, authentication, and other. And as gRPC is designed to be pluggable and customizable, there are other companies and developers that contribute to gRPC ecosystem. And we want you to contribute as well. You can check out gRPC ecosystem GitHub repository and make gRPC world even better. So please try it out. Check gRPC website, clone gRPC repository, follow gRPC on Twitter. gRPC-IO Google group is one of the best way to reach gRPC developers and users and ask your questions. And don't hesitate to contribute again if you find it useful. To summarize what have been said, gRPC is a high-performance RPC framework from Google. It gives you bidirectional streaming with multiplexing over one single TCP connection. It's built on top of Netty that provides you asynchronous and non-blocking I/O. It supports deadline and cancellation propagation, flow control, pluggable service discovery, and load balancing. It's available in at least 10 programming languages. It's stable, production ready, and has growing ecosystem. And thank you everyone for being here today. I hope it was helpful, and I'm ready to answer your questions.